Yeah, I'll give you a thumbs up when we're live.
Hello everyone, welcome back to Kent Seminar. We have a bunch of very good and exciting speakers this semester. Professor Hajj is one of them. He graduated bachelor's at Virginia Tech, then went for master's and doctoral degree at Texas, at Austin, and now he's an assistant professor here. And he's here to talk about materials, about asphalt, and basically a fundamental study of how asphalt fails. So let's give a warm welcome to Professor Hajj.
All right, thank you so much. It's great to be here kicking off the Kent seminars. So I'm excited to give this talk. Basically today I'm going to talk about the work I did last few years in my master's, PhD, and now starting to work on here at the University of Illinois. So I wanted to get started first by thinking about pavement engineering as a field, kind of where we're going, at least from the materials perspective. So it's not a full roadmap, but just from the materials perspective, what are we thinking about in pavement engineering right now? So in the past, and this is what most of my work has focused on so far, we focused heavily on characterizing the resistance of the materials to two distresses, rutting and cracking. Other distresses too, but those are kind of the primary ones. Because we want to have kind of some kind of method to choose what materials are the best to use. So this has become kind of routine in our field, and everybody comes up with, hey, this is the next new method, this is going to be the next big thing to characterize rutting and cracking resistance in the material. But as we're moving on, we need to think kind of further. How are we going to engineer better materials? Now we have a lot of the concepts, we understand a lot of the mechanics, we're still understanding a lot of the mechanics that we don't, but once we have those concepts, what we need to do next is start engineering better materials. Smart materials, self-healing materials, higher amounts of recycled materials, all of those kind of things. Technologies to lower emissions in the production phase. All of those things we need to work on engineering those better materials and technologies to enable a future of pavements that are more durable, smarter, and more sustainable. So I want you to keep that in mind as we're going. Keep this half of the presentation in mind, although a lot of it will focus on what we've done on this end. I just want you to kind of start thinking about how we can use those new concepts to do this. Great. So this presentation, like I said, is going to focus more on where we've been, that side, and then in the future, at the end, we'll talk about that side. So this is kind of a roadmap that I have for the presentation. I'm going to start out giving a little bit of background. I think most here are familiar with asphalt, but there may be some watching who have some questions, so I hope I'll answer those. We're going to talk about some of the computational modeling we've done, in addition to the experiments at the micro scale, and then I'll talk about some other studies that we've done that have been interesting, and finally the future and where we're going. So, starting off with the background. What is asphalt binder? And I apologize that this is starting very simple to those who are very familiar. I just want to make sure we're all on the same page first. So it is a binding agent in flexible pavements. Flexible pavements are made out of, by weight, usually about 95% aggregate, 5% binder. So both are tremendously important. The binder is kind of the glue that holds it together. Generally the binder can occur naturally, but more often it's obtained from the fractional distillation of crude oil. It's kind of what's called the bottom residue, so all of the lighter fractions are used for petroleum production, the high value stuff, and then what's left over at the bottom is the asphalt. Got a very complex hydrocarbon chemical structure. We'll talk more about that later. It's thermoviscoelastic, meaning it's temperature and rate dependent. So kind of what makes this unique among other construction materials is that it does have that rate dependency and temperature dependency as well as a huge issue. Each source, and even two binders from the same source but different batches, have very different properties. And that's even if they're the same grade. So we've got a lot of different asphalts with a lot of different properties, and basically it becomes very hard to characterize them. It's not like a cement plant where there's a very specific recipe, although that can vary too. There's no specific recipe for asphalt, and it's kind of a black box in terms of what goes into the material. Especially most of this work was done in my graduate study at Texas, And in Texas, we allow any modifier as long as it passes the spec. So it's not like here in Illinois where there is limits on what you can add. It's mostly polymer. In Texas, you can add absolutely any modifier as long as you still pass spec. So it's something we're thinking about and something we have to be conscious of, that we don't really know what's in it when we receive a binder. And generally, the binder is thought to control cracking in the mixture. So when we talk about cracking, often we're thinking that cracking occurs through the binder because it does have a lower strength than the aggregates. So the current cracking specification, this was developed as part of SuperPave in the 90s. A lot of hard work went into this to replace using penetration and ductility, penetration and viscosity. And when we replaced those, this was a huge improvement for neat asphalt binders. So that's the key thing. Basically, the current specification says you want to minimize this parameter, G star sine delta. G star is the stiffness of the binder. It's a rate-dependent modulus of the binder. In this case, we're only measuring at one specific rate. And this is, of course, based on linear viscoelasticity, so that's important. Then delta is the measure of elasticity, the phase angle. This is based on how much the material is behaving like an elastic solid versus how much it's behaving like a viscous fluid, from 0 to 90 respectively. So, in the end, we want to, generally, the conventional wisdom is we want to minimize this parameter. We want to lower stiffness so that the binder can deform and have a higher ductility before it fails. And we want a more elastic binder so that it can recover those stresses that are on it more quickly. However, there are some drawbacks. This technique only measures the linear material properties. We actually don't touch strength even. There's no strength-based specification right now for asphalt binder, so we're not actually measuring what's happening when a crack is occurring, or when we think is a crack occurring, and what we've investigated here. So this is a big issue. The other thing is, of course, that the stress state is unrealistic. For those who have worked with this parameter before, it's done, of course, in the dynamic shear rheometer, which uses a parallel plate geometry of 2 steel plates with a 1 millimeter thick specimen between them. And the problem there is that you don't get a uniform distribution under that plate of stresses, and also that stress state is not realistic. We'll talk more about what is a realistic stress state in my presentation. And finally, this specification was developed for unmodified asphalt. So all those correlations and things that went into this were for unmodified asphalt, but of course nowadays we're using modified asphalt, we're using recycled asphalt. We're in a lot different of a place than we were 20-ish years ago when this was developed. So why is the stress state important? Well, in asphalt studies, if you search asphalt temperature dependence, asphalt rate dependence, asphalt aging on Google Scholar, you will find hundreds and hundreds and hundreds of studies on those things. Those are commonly checked for binder, and those have been studied to death, basically. However, stress state's often been neglected. So most studies didn't consider the importance of stress state on the failure. Where do we see the stress state change in the material? Usually we're thinking confined films of binder between 2 aggregates. That's where we're going to start to see a different type of stress state. In that stress state, we expect to see a high triaxial state of stress. And this high triaxial state of stress, basically I had to go to other fields to learn about this because there wasn't much in asphalt. When that high triaxiality starts occurring, you end up seeing a loss of ductility and a change to the strength. And actually some studies said in material science that you cannot measure ductility unless you've considered the stress state. Otherwise, your ductility measurement is meaningless. So this is a big change for what we've been seeing in the asphalt world thinking about ductility because we've not considered the stress state. So how do we define triaxiality? The most common way I found in the literature, again from other materials, asphalt researchers didn't do this too much, was to take this triaxiality factor, which is the hydrostatic stress divided by the von Mises. So that's kind of what people are commonly using to measure triaxiality in other fields. So we wanted to create a computational model to determine what is the stress state of the binder in the mixture. So how did we do that? We did a multi-scale analysis. First we started with a full pavement model. This is based on the work of 2 different works, one from Texas A&M, from Professor Little's group, and one from Hao Wang, who was previously a student here and is now professor at Rutgers. So we based our full pavement model on that, a very simple pavement model just to see what's kind of the triaxial stress state on the mixture in a pavement structure. Then we took CT scans at 2 different scales. We took CT scans of a full mixture, and we took a CT scan, this is just a typical dense graded mix, CT scan of a FAM or mortar specimen as well of binder. and fine aggregate. So the first one is a full mix, and we separated it into coarse aggregate and mortar. Second one is a FAM mix, and we separated that into fine aggregate. And then the mastic, which is just the aggregates below 75 microns, so basically the fillers plus the binder. So in the full pavement model, we computed principal stresses to determine kind of what's that triaxiality factor. And we found basically what you'd expect. We found high tensile stresses at the bottom of the pavement layer, leading to bottom-up cracking. We found heavy compressive confining stresses in the third direction due to the tire load throughout the pavement structure in this case. And of course some shear stresses on the side that could lead to top-down cracking. But pretty much, at least for this pavement structure, we saw bottom-up cracking is kind of controlling the failure. And what we noted there is that the triaxiality is pretty low. There's not a high hydrostatic stress if you consider the asphalt as a continuum. Triaxiality factor overall is pretty low. So now we consider the computed tomography models. So we use X-ray CT. I won't go into too much detail about the method right now, but basically the idea behind CT is you use an X-ray beam to pass through the material at all different directions at different heights, and you create 2D slices, quote unquote, of the material microstructure so you can investigate it more. So in this case, we're using X-ray CT. We're picking up 2D slices of the material. We binarize and segment those to separate the aggregate from the binder or mortar, depending on what scale we're working at. We stack them to form a 3D microstructure and mesh that and use that for finite element analysis. So what did we find here? We called these critical points, where we found almost stone-to-stone contact with just a very thin film of binder between. We found extremely high local stresses, in sometimes 10 times as much local stress as the bulk stress that we applied. And we found high confinement, meaning high triaxiality at those points, very high hydrostatic stress. And of course, at the smaller scales, as we went down in the scale size, we found even a higher triaxiality. So for the full mix, found something around 1.1. Then for the FAM mix, we started finding 2.2. So we're theorizing that actually as we start to look at what's that stress on the binder, it's actually going to be even more of a triaxial stress state than we previously thought, just based on the mortar and the coarse aggregates. So one way to represent this in the lab is this poker chip test that we've used. So we also just ran a quick FEA on this poker chip geometry. And what we found, of course, is that it's very dependent on the thickness of the film. So actually the triaxiality in the center doesn't change much, but what you see is you start to see a non-uniform distribution when you use thicker films. And this is closer to the DSR than this. So if you use a thicker film, you'll see a very non-uniform state of stress, which has been shown by other studies too and solved analytically. So we want to emphasize that, if you're going to do strength testing and you want that realistic stress state, the best way to go is the higher aspect ratios, 50 and above, to be safe. So of course we proposed this poker chip test, which we do using a DMA. And basically we confine a thin film of binder between two steel plates. In this case, we're just looking at cohesive failure, so we don't care about what's the interface. We just want something stiff and something that bonds well. So we bond it between two steel plates, and we pull it apart. We do a monotonic tensile test, pull it apart, and we get a failure surface that looks like this. So this typically comes with a stress strain curve, but the next part of the study we wanted to investigate a little more and understand why we're getting what we're getting here in this test. So our experimental investigation. Excuse me. What we ended up doing, we found that binder kind of has two main instabilities that occur. So you've got the cavitation instability, and this could be considered a very brittle fracture. So when do we see cavitation instability? Intermediate to lower temperatures, thin films, and high rates of loading. When do we start to see this bulk fingering or bulk deformation instability? This is at higher temperatures, this is at lower loading rates, and this is at thicker films. So what we notice here is interesting. Actually, this test was run in DSR because that's where we could create a thick film and load it slowly. That DMA capability was okay. So this was from DSR. This is from our DMA. And what we notice is when we start to raise that aspect ratio higher, which means thinner film, the strength of the binder gets pretty uniform and it's higher. Then when we go to those thicker films, so this is everything else is the same except for the film thickness. So this very low aspect ratio, which is defined as diameter to thickness, so it's a thicker film basically, we start to see that transition from cavitation more towards flow or deformation in the material, and we start to see that strength decrease a lot. So we kind of theorize, that this is where we're going to be looking at cracking occurring, is in this range with the thinner films or the higher loading rates, advanced ages, etc. So we, of course, need to observe the microstructure to understand this mechanism, how these instabilities happen. One technique that's commonly used is atomic force microscopy, but it has some drawbacks. So for those who aren't familiar with AFM, it's a little probe that you use to measure the stiffness and measure the create a surface map of the surface of a material. But the specimen prep is very difficult. You can only look at room temperature because you can't heat or cool when you're using this atomic force probe. And you can only observe the surface structure. However, what we found when we observed the surface structure with a light microscope, we found that actually the surface structure is entirely dependent on what the interface at the surface is. So these famous B structures that you see in asphalt binder that form at the surface as you cool it, these only occur if it's an air binder interface. So if you just put glycerin or water at the interface, actually these structures are completely suppressed, which makes us think it's just an artifact of the surface tension. It's not an inherent material property. So instead, we use dark field optical microscopy, and these images, we worked with a group in physics who are brilliant in optics. They helped us to use this method that scatters light at near infrared, and whatever's reflected back are those microstructures about 25 microns deep into the material. So it's not what's at the surface, it's actually what's in the bulk of the material. And what we found interesting here is that those inclusions that we see are not dependent on the surface conditions. So it actually doesn't matter if you have water, glycerin, or another solid at the surface. So you could have it, for example, between two glass slides and still pick up that microstructure. So we think this is more of an inherent material property. Our group also did some study that found that this is related very closely with rheology in terms of thermal loading cycles. That's another paper that they did back when I was a master's student. But this was very interesting to us, and we decided to use this technique to actually explore the failure of the material. So we developed this apparatus. We confine a thin film binder, similar stress state to the poker chip. We place an actuator attached to a plexiglass cylinder so that it wouldn't scatter light. And we put it on a thick plexiglass slide so that we wouldn't fracture the slide when we start deforming. And then down there you can see our light source and our objective that's picking up the images because it's attached to a camera. So this is the stress strain curve measured in this test at two different loading rates. So you see 1 micron per second and 5 microns per second. Typically we see higher strength for higher loading rate, which is interesting because cracking resistance, we often think lower loading rate will lead to better cracking resistance. Not always the case. I mean, maybe not the case because we see higher strength here. Anyway, we took these images as the failure was progressing. So this is for the 1 micron per second. In the linear viscoelastic range or undamaged state, you really don't see much. Actually, those bulk microstructures are here, but this is only 10x illumination or 10x resolution. So because this is 10x resolution, you can't see the microstructures clearly, but if you look carefully, you can see that there's clouds of them here. So we do see them, we just can't see them very clearly, and the slide doesn't show it as well as my computer. Then as we hit the peak, we see a few cavities start to open, so we actually start to see those first appearance of damage as we're close to the peak. Then as we start going on the other side of the peak, this is kind of that post-peak failure. We start to see more cavities form. By this point, they're pretty much done forming when we hit that inflection point, and then finally, they keep growing, but no new cavities can form. So we kind of put this as a 3-stage model. We kind of decided that that's what we can consider it. First stage is the undamaged state here. Second stage is post-peak where new cavities can form and damage is nucleating pretty rapidly. And then third stage is going to be when no new cavities can form. There's not enough energy to actually form new surfaces, but there is to grow the existing ones. Then we looked at 5 microns per second. We said, does the same thing happen there? Answer was yes. So again, undamaged state. Peak, you can see that first hint of damage, but not much. Then post-peak, you start to see a little bit of damage appear, but not nearly as much for this 5 micron per second. but it does make sense because we're still got plenty of strength here. A few more form by the inflection point, and then finally you see those few cavities that are there grow, but no new cavities form again. So very similar at 5 microns per second, but what's interesting is we do see a lot less damaged surface. Of course, one inherent flaw here, you can only capture one field of view as you're going, so we don't know what was happening outside of this field of view, but it definitely looks to us like less damage is forming. What about fatigue? So we started running fatigue experiments. This is 50% strain amplitude at 10 hertz, and this whole GIF is 30 minutes real time. It's about 30 seconds here, it's about 30 minutes real time. So you can see those cavities form after many cycles, and then, or after just a few cycles, then after many cycles, they actually start to form a little crack, and you can see another crack there. So it looks like these two cracks from two different cavities are actually connecting. And this is kind of how we can say, okay, under fatigue, first we have cavitation, that's the first form of damage. But then after that cavitation and those cavities grow a little bit, we actually start to see the nucleation of what are micro cracks, and then finally how they connect and grow into macro cracks. So this was very interesting to us because it gave us some insight into what is the fatigue mechanism. Now the caveat here, usually with fatigue experiments, you need some kind of notch or some kind of initial seed for damage. In this case, we did have to apply some load and get it past the post, get it up to the peak so that a small cavity would form to see any damage. Otherwise, there was nothing visible, which was very interesting. Of course, there's a very high loading rate too, which again corresponds with quite a high strength here. So something to think about. Now we said what happens if we apply higher amplitude, longer amount of time. So this is 10 hertz for an hour at 100%, and you can see very quickly those cavities collapse and start forming cracks, reaching other cavities, and basically forms a network of cracks, or what we could consider kind of macro cracking quickly. You'll also notice that those bulk microstructures, they start shifting away from where those cracks are forming and shifting into the areas that are undamaged. So all of those microstructural features kind of tend towards those undamaged regions, and those damaged regions, you start to see those microstructures aren't really there anymore. And we wanted to say, what about healing? So where can you still heal? Where can you recover the damage in the material, and where can you not? With cavitation, we usually saw that the material could pretty much fully heal or leave just a very small cavity. But in this case, we left this one rest for 3 days, and we saw those cracks didn't heal. So that appears to be more permanent damage, what's done there. At least without heating or anything, you're gonna see those as permanent damage. And as you can see, those microstructures still stayed in the undamaged region, away from the cracks. So it was very interesting to us. It gave us some insight into the healing mechanism too, and when the damage becomes non-recoverable. Okay, so what about the initiation of damage? So in this case, we wanted to say where are these cavities forming and why. What you notice is you've got this point here, and then once we apply some load and get up to peak, it actually forms a cavity right at that inclusion spot. So we thought that was very interesting. It forms at the inclusion, not in the matrix. Why is that? Well, we went back to some classical mechanics solutions by Eshelby, and in this case, what we saw here is that if you're given the stiffness of the matrix and stiffness of inclusion within a matrix, you can kind of define what the local stresses will look like at different points within the matrix. And what we found is, based on this equation, if the inclusion is stiffer than the matrix, which kind of goes along with the conventional theories that the inclusion should be stiffer than the matrix, then actually you will see that first seed of damage occur at interface between matrix and inclusion. That'll be the highest stress point within the matrix, right at the interface of the matrix and inclusion, which makes sense then why we see that damage appear basically at the point of the inclusion. So when there's a very high local stress at that interface over here. So that's kind of what we theorize, is that those inclusions are the stiffer fractions of the binder. But of course now we need to validate that, and we're working on experiments right now to look at what's the stiffness of those different constituents in the bulk. So that's one thing I'm working on right now. Okay, so now just to jump into some other studies that we've done, different studies that I worked on throughout my time as a graduate student. One thing was, of course, implementing this poker chip test. So, you know, there's a lot of fundamental research that went into this last things that I presented, but one of the most important things to always consider is what's applicable immediately. What's a quick test we can give a DOT, let's say, to use as a screening tool? This was one that they really liked. Basically, we had a project where we had a bunch of binders come in and we were just trying to screen them and determine which ones had something strange going on, had kind of those things that raise the alarm bells. Up here we've got 4 binders, all grade PG64. Then these are all grade PG70, all minus 22. So these are polymer modified, these are not polymer modified. And what we notice immediately, this is actually a binderized image of the cavitation surface. This binder 3 is a really strange one. It had very small cavities and very high number of cavities. So we said, why is that? What's going on there? When we took measurements, it also had an incredibly low strength compared to other binders. That's basically what this graph means. You can see a very linear relationship for the others, and then just one random point here, that's binder 3. That's because of a very low strength compared to other binders. It was about half as much as other PG64s, roughly. So we said, wait a minute, what's happening here? It's passing the spec based on linear properties, but it's got a horrible strength. And so we ran an XRF analysis, and we did find some trace metal content here. Combined with that cavitation, we said, hey, this poker chip test could be a good identifier for those kind of unsavory additives. And again, this is super important in Texas because you're allowed to modify your binder with anything you want. We're not limited to polymer there. You can actually modify with any modifier. So we knew that there's some modifier that is maybe leading to a really bad result in strength, but they're able to pass it through the PG system still. So this test was really successful. We also showed a pretty nice correlation with Texas overlay test. Okay, you might say, oh, wait a minute, 0.67, that's not amazing. But you have to consider with these, this is the critical fracture energy from the new overlay test spec, which is much better than the old one. And these are 16 different mixture types. And in these mixture types, we had different amounts of wrap brass, different additives. Some were polymer modified binders, some were not. Different aggregate gradations and different aggregate sources. So all of those confounding variables, and we still saw some link. We extracted those binders from these 16 mixes, and we still saw a pretty good relationship between binder strength and mixture strength, or mixture fracture. So we said, not bad. TxDOT really liked this. They've actually issued since a implementation study for the poker chip test because this was the only test that showed any correlation immediately with these. We tried a lot of other binder tests, which I won't mention the names of because it will just insult the people who came up with those tests, but we did try almost many different binder tests and we couldn't find any good relationship with an R² above like 0.1, except for this one. So that was a really nice finding that really gave them something quick, easy to implement. The only challenging part about implementing the poker chip is you do need a different equipment. So the DSR isn't gonna work for this. But one option, there's an equipment called the PADI that's been used for adhesive testing, like as a pull-off test for binder and aggregate. If you just adjust the loading rate on that a little bit, you can use it as a cohesive test as well, or the film thickness. Here's a project we did on dispersion of nanomaterials. So nanomaterials in binder was a really, really hot area for a while. Still is to some extent among producers, but most people are realizing the costs are pretty expensive. So one thing we did here, we wanted to say, wait a minute, are these nanomaterials actually acting as nanomaterials, or are they not able to disperse in the binder and are they clumping together? So we took TEM measurements of 6 different nanomaterials. 2 of them are functionalized. And basically what we see here, they're about 20 nanometers in diameter, each material. One of them was large, but the rest are about 20 nanometers in diameter. So not a bad, it's nano size. It's on the tens of nanometers scale. But we said, asphalt is very difficult to disperse things in, right? Because asphalt has such a high viscosity, it's not an easy medium to disperse things in. So we said, why don't we take some solvents with a similar polarity to asphalt, things like toluene, TCE, whatever it is, and if these can't even disperse in those surrogate solvents that have a low viscosity, there's no way they will disperse in asphalt, right? So what we did, we used dynamic light scattering combined with a dispersion test, and we measured what is the hydrodynamic radius of the particles we're seeing. You can see that some of them are super high, 3,500 nanometers, which is 3.5 microns. So we're suddenly seeing these 20 nanometer particles, we're seeing them as 3.5 micron particles there, which means that they're actually not even acting as nanomaterials anymore, they're acting as micromaterials. And why is the reason for that? Well, that means they're not dispersing, they're clumping together. We're basically seeing all of them form a little ball, and they don't disperse even in these solvents. All these different N-heptane, in this case N-heptane and isooctane, but we tried a couple of other solvents too, and we saw consistently that the dispersion was not good. Now the ones that did disperse the best, a couple hundred nanometers, so still not perfect dispersion, but better. We did see some relationship with the properties at all, especially on the low temperature side, that they did have some improvement. The others actually were hurting the low temperature properties, which makes sense because they were almost acting like a filler instead of like a nanomaterial. They were not a well-dispersed nanomaterial, they were acting as a mineral filler, which basically, of course, if you add filler to binder, you're gonna get a worse binder performance test on low temperature side. One other project that we worked on, this had to do with ultra-thin overlays. So ultra-thin overlays, the idea was basically we needed an alternative for chip sealing. For those who don't know, chip sealing is kind of a surface treatment that's used for lower volume roads. Basically a layer of binder and then you spread a single size aggregate on top. And we wanted to come up with an alternative for that for a lot of reasons, but mostly financial, because now this there's a piece of equipment that is used to apply ultra-thin mixes, and actually it's patent expired, so TxDOT was saying, well, now we can implement this and you know, maybe use these mixtures a little more. So we did a lab study where we tried 6 different gradations of ultra-thin mix with polymer modified asphalt, and we did 3-wheel polishing tests, so we just polished and measured the friction with dynamic friction tester every certain number of cycles. And what we found, actually, this is kind of the normal coefficient of friction for chip seals, or seal coats, whatever you want to call them. 3 of 6 mixes lasted the whole 100,000 cycles in terms of not having any raveling or bleeding. And they also ended up having a final, even after 100,000 cycles in the 3-wheel polisher, a better coefficient of friction than what we typically see for chip seals. And since these are only ½ inch, they're pretty cost effective. We did a cost analysis. Roughly, you're looking at similar costs to chip seals, so not too much. You can definitely use a ½ inch HMA layer. So this is just kind of another project that definitely applied some, had some real-world application quickly. So now, I just want to conclude by thinking again towards the future. So, again, we come back to this slide. This is where we've been, this is what we've been doing. But we want to definitely get over here. So right now, we're thinking we have the computational techniques, we have the fundamental techniques, microscopy, those kind of tests. We have all those fundamentals that we know to be true, the physics, the chemistry, all those things that are involved. We still have a lot of work to understand those, but as we're understanding those, we can use those to develop these new technologies. And I want to encourage everybody to always think, you know, what if we ran out of asphalt tomorrow? We need to have a building material that's ready to go in place. We're not going to run out of asphalt tomorrow, but it's going to happen one day.
Just concrete.
Don't say that, don't say that. That's the worst answer, Isaac. So we need to have a building material that's ready to go, that's not concrete. So, okay, let's say a sustainable material, so that rules out concrete. And so we need to have a sustainable material ready to go. So that's what I want always everybody to be thinking about in their research is if this material wasn't in existence, how could I characterize something new? How could I use those same tools to discover something new and to create an alternative quickly and efficiently? So I hope that's what we're going to do, and I hope that's the direction we're going to move in the future in our field. And I think that will do us a big service. I love asphalt. I don't want it to go away. I just want to always be thinking about the next big thing and how we're going to make things better in our community and better in our infrastructure. So of course, I just want to conclude by thanking, of course, Dr. Basine, my advisor. He was instrumental in all of this work. None of it would have been even close to accomplished without him. A couple of students who I worked with, there are many more, but Angelo was kind of working with me since day one. We worked together a lot on different projects and papers. Adam is a student from physics who now works at Intel. He was kind of the mind behind all the optics stuff that I didn't understand and helped to get me up to speed there. Professor Mike Downer from physics, he is just a genius in optics and probably the only guy I know who has almost as busy of a schedule as Professor Al-Qadi. And all of our collaborators, we just had so many great students, undergrads, grad, technicians who helped us along the way. Could not have done it without them. And then of course our sponsors, TxDOT, NSF, Ergon, and the Robert Welch Foundation, who were really generous in funding this research. And I am happy to take any questions that you all have.
first one is related to the first part that you were showing, related to the triaxiality of the load, and this is something very important because it affects really the behavior of the material. We worked on a project that is not published yet, but it's related to the same topic. But we did it in a different mentality. So what you did is you had the material property as linear viscoelastic, which is characterized without triaxiality. It's just you're applying like uniaxial loading. And then you check the triaxial load. But what we did is we rendered the dynamic modulus with confinement. So we developed a model for confinement-dependent linear viscoelasticity, which becomes not really linear because we introduced nonlinearity. Now what we did is we developed a UMAT for abacus that does the nonlinear, the confinement-dependent nonlinear viscoelastic. And this is how we saw it, because the way that you showed is you're keeping the material property the same and checking the triaxiality, but the triaxial load will affect the property of the material.
That's true.
So there is like a full cycle that we covered.
Yeah.
My second question is, when you were showing, because maybe I missed it, when you were showing the picture of like the micro and the micro damage happening, can you please go back to the slide?
Back that way. This like GIF?
Yeah,
or okay.
But you were showing on the curve, yes.
Sorry.
Yes,
Yeah.
this one. So here, maybe I missed it. So where are you located? Where is, what we're seeing is where within the specimen? And how did you make sure that the location is like very close between the two when you were comparing?
Yeah, so this is a good question. So just first with regard to the first point, the triaxiality in our case actually, I think in your case it's an input, in our case it's the output. So we're actually trying to determine what is the triaxial state of stress. I think in your test you're trying to determine what is the material property based on a known triaxial state of stress.
No, this is not what we did. What we did is we characterized material in the lab as a triaxial, then we checked the triaxial state. Because the triaxial state depends on what material property you include.
That's
you
true.
Include
That's
it
true.
Without triaxial, without the effect of
So
confinement.
we have to make some assumption. In this case, like for modeling, we cannot first check in the lab. So we had to make some assumption, what is that material property? So we just assumed the regular linear, which, yeah, of course, you're right. But also the model uses linear viscoelasticity first. So we're not thinking about triaxiality. Mostly the effect is going to be on the nonlinear more. The state of stress is going to more have an effect towards the nonlinear side than the linear, from what I've read, in terms of ductility, right? So this is going to be mostly post-peak behavior. So that's why we didn't, we said, okay, it's good enough to assume the linear viscoelastic. You're right, it's not the same material property, but we have to assume something to input into the model because that work was all done modeling. So, but yeah, this is a good point. So you do need to always consider what is your triaxial properties. And yeah, you're right, actually it's a little bit hypocritical to say, tell everyone else you need to consider triaxial stress state, but then we did not use triaxial material properties, but that's just because we don't have them in the model. Now your second point, okay, so you were saying how do we make sure that we're capturing the same field of view for both specimens?
Yeah, where was it in the specimen?
Yeah, so actually what we do is we have a, like, where that, sorry, let me go back to the input of here. There we go. Let me go back to the apparatus. So this is physically, it's not shown here, but this is physically restrained, like the actuator. So when you put that cylinder in, there's a little hole for that cylinder to go in. And actually the cylinder will always go in the exact same spot. So the binder specimen is directly under the cylinder. It's bonded between the cylinder and the plexiglass slide. So it cannot go in any other position. And this actuator is like fully restrained. So it laterally is fully restrained, so it cannot move. Only the actual like little bottom piece can move. So it's always going to be guaranteed to be in the same place. And then we are able to adjust the position of the objective here. So we just have it noted where the objective needs to be to capture basically the center of the specimen. And we know that because we know our specimen diameter. In this case, it was 8 millimeters, I believe. And so we know our specimen diameter. So if we get to one side of the specimen, like the end of it's a cylindrical specimen. So if we get to one end of the cylinder cross-section, then we can measure exactly 8 millimeters from the other and find our position. So we just locate it digitally using that.
Just one more for all.
Yes.
So how do you make sure that whatever you get here as damage and as like whatever is happening at the microscale level or whatever you're seeing there applies also whenever you have a mix because the mix the issue might like the crack might initiate between the contact between the binder and the aggregate,
Yes.
which might change whatever results that you see. The ranking of binder might be different whenever you include it as a mix.
Yeah, this is a very good point. So actually, there is no way to say that this is gonna for sure predict mixture cracking. And probably that's a big reason we don't see perfect correlation between the mixture, because actually much of the mixture cracking is an adhesive problem rather than cohesive. So for this one, we are thinking just to develop a test for binder screening, maybe before you've even chosen the materials for the mix. For mixture, if you actually want to predict mixture cracking, you have to consider both cohesive and adhesive, which means you need some kind of adhesive test. A lot of people have worked on different methods like surface-free energy and that kind of stuff to look at adhesion. We didn't work on that part so far, but yes, you're right. You need two different methods. You need to characterize, I think you have to characterize them separately. You cannot characterize them both in one test because there are too many variables to predict which way it's gonna fail. So I think you can predict first the cohesive response and say, okay, this is the ranking by cohesive performance of the binder. Then you can take your binder and aggregate material and say, okay, this is the adhesive performance of the materials. Angeli?
Would you mind going to the video?
Yeah.
Really nice work, first off.
Thanks.
And then regarding, so one of the questions is, I don't understand why the illumination, obviously it's indicative of the cavity initiating, but then it also becomes black again, and then it follows the crack. Could you just give a detail? I don't understand why that illumination disappears as it's moving.
Yeah, actually this was a big question for us too, and we're not quite sure, but yeah, you can see, so that illumination starts to go. I think part of it is the microstructures moving away from the cavity. So in those first few cycles, those microstructures don't move yet, so those microstructures become exposed and heavily illuminated based on the damage. But a lot of that illumination is also from the bottom plate. But the way that dark field works, it basically, like, if there's something scattering brighter, it will focus on that instead. So, for example...
That's due to the movement of the microstructure.
Sorry?
The movement induces that illumination?
I think what that illumination, like when it's very bright like that, I think that's actually the bottom of the back plate scattering, like the top plate. You're seeing the bottom because now there's a cavity there, so there's just such a thin film of binder that actually you're starting to see the bottom of the top plate through that, because the camera's coming from below, and then on top you've got it sandwiched between the cylinder and the slide. So actually you're seeing the bottom of the cylinder, which is scattering a lot. So I think that's what's causing that bright scattering in the beginning. But basically the way that dark field works, like what I was saying, is that when something else starts to scatter more, then it takes away from, that becomes the thing you see primarily. So I think that's why when these cracks start to form, those start to scatter even more, maybe because of a rapid movement of microstructure or a combination of that and the back of the cylinder becoming visible there too. So that takes away from what you see in the cavity. But there's not really a good way that we found yet to verify that.
And as the snapshot progresses, are you able to characterize what you're looking at, apart from the inclusion, to kind of define, you know what, around this area, 1 to 2 or 3 even cavitations can predict, because you have the data transiently to kind of track that and identify those characteristics. Yeah,
we did. Actually, one thing we looked at, it's in the paper, but it's not in this presentation. One thing we looked at is, like, once we start to see, need to go back, like many cavities form, and it's in our paper that was in IJPE last year, when we start to see them form, like with the growth rate. So we started to characterize each cavity that we could see fully in an image. We characterized the rate of growth and when they're forming, and this actually helped us to separate into that 3-stage model, but also to verify some of the theory that had been seen in other materials. So in those polymeric materials, they do a lot with, like, the growth rate and why they grow. And basically what you see is those cavities that form later, they actually grow faster, but that's only until they run into another cavity. So that's the big issue we saw there. It's like this one, for example, this small one, it grew quite a bit from here compared to its counterparts, but then it started running into this one and stopped growing. So we did characterize things like that, and it's in the paper, just didn't present it here. Yeah. Other question? Yeah, Javier.
So from these pictures, you were saying that the brighter light is coming from the plate.
Correct, yeah.
So is this stress adhesion or cohesion or a mix of them?
So this is cohesive failure, but what happens is actually like it's cohesive, but it's such a thin film that once it starts to fail cohesively, there's just a very thin, even like just a tiny thin part of binder on the other side of the plate. So we do define it as cohesive failure, but what ends up happening like within that film, it's then created a cavity that has some, it's not a two-dimensional cavity, it's three-dimensional. So there's just such a thin film of binder at the top that you can actually see the back of the plate through that binder. It becomes transparent enough that light can scatter behind it.
Were you able to verify that there was binder?
So what we did is we used the exact same aspect ratio and loading conditions as a poker chip test.
Yeah.
And in the poker chip test, with those exact same conditions, the only difference being it wasn't done on the microscope,
Yeah.
we did verify that because we looked here, like these images.
Oh, it looked like the one on the right.
Exactly, on the left.
On the left?
So yeah, the one on the left. So actually, you do see this. There, we put a white powder so you can see the difference, but you can see on the back like there is binder underneath the.
Yeah, I cannot see the plate, you're right.
Yes, yeah, you cannot see the steel plate, right? So you don't see any steel, so you do see binder. But if you look at it under light, you can see also that binder is pretty thin, so it's transparent. But there is binder left, so it's cohesive. So we do verify that it's cohesive in the poker chip test, just to be sure that that we're not disadhering from the plate, because we use the exact same testing conditions in that one: temperature, loading rate, everything, aspect ratio, everything.
Could you go back to your stress strain plot?
Yeah.
That one.
Yeah.
You always define the failure strain that you showed after.
Yeah.
Was it the peak strain here?
Okay, so failure strain, you mean when we did the implementation study? So that was a little bit different. That was part of a work that was done at my master's. That was done with the stress control test instead of strain control. At the time, we had been suggested to do stress control by a colleague who turns out later actually that it wasn't a good idea. But basically, he told us like, do stress controlled instead of strain controlled.
Yeah.
So we applied a rate like 1 Newton per second instead of 1 micron per second or what it was. So when we did that one, this stress strain curve actually like it just comes out something like this, and then it abruptly ends. So you see like basically like a ductile response, increasing strain, and then you just see the strain kind of continue and continue, and then it just abruptly fails, and that's like the end of
Like
the
when
test.
the material is separating.
Exactly.
Totally.
Yeah.
And that's what you define as.
And that's what we defined as a failure strain when that final point was like, it was more of a ductility measure in that case. It was like, it looks like the plot of a ductility test more than anything else.
And when you did these kinds of tests, did you see any binder flow, like a plateau on that peak?
There was one binder. I don't know that it was flow necessarily, but it had almost what you would describe as like a plastic response, like a high plasticity, because actually it got to this point and then it kept, like it had a change in slope, a pretty drastic change in slope, but it did have like quite a much more deformation before it started decreasing from the peak. So the peak was like way over here, like at 80%.
And what was happening on the images to that one?
So on the images for that one, we didn't see any observable damage really until almost the peak at 80% or so. We still didn't see it even in that like plastic phase. So we were thinking that was just like deformation, but no damage observable until the actual like still then it did hit peak around 80 and started decreasing rapidly. So then we started to see the damage. So that's when we say for sure that there is like damage based on the images too.
Was it a modified as well?
We don't know, so these were just obtained from producer and we didn't ask. It was PG64, so we think no, but in Texas you see a lot of blending too, so it could very well have been polymer modified, and that level of elasticity does make you think polymer modified, right? But so it could be a 70 that was blended with a 58 to reach 64. That's common in Texas. But if it was a neat 64, then for sure it wasn't modified. I mean, that's generally not modified, but we don't know because, like I said, binder is a black box, especially in Texas. We don't have any idea what's the modifiers. So what's interesting is that the lower rate, it showed a normal response. So that was only at the higher rate of loading that we saw that too. So something strange was going on there. Yeah. Yeah,
And
Puneet?
maybe I missed, what aging conditions did you use for these testing?
Okay, so these were just unaged binders.
Oh,
Yeah, so these were just unaged binders. So that's a good point too, is that the aging condition has a big influence, just like the temperature, loading rate, triaxiality. But our kind of theory here is that in the end of the day, a crack is a crack. And it can occur, it doesn't necessarily occur in the, I mean, we always assume PAV is going to lead to cracking, but it doesn't necessarily occur in the later stage of life. It could happen in any stage. So we just said, you know, especially if we're going to be doing these very high rates and we want to prevent adhesion, we want to use the unaged data binder. We did run some tests later on aged binder. I mean, we've run a lot of poker chip tests on aged binders as well. And we do see that strength continue to increase, but also like much more rapid decrease, like a loss of, you would say a loss of flexibility probably.
and how the failure mechanism, like cavitation process, does it change significantly with aging, or is there some other response? Because at like unaged condition binder, I mean, the cavitation process might be a little different than
Definitely. So what we notice is a lot, like the failure does, first thing is that a lot of it does become more adhesive, so we do start to see the metal in the plate, like when we do a poker chip test. In terms of shape and size of cavity, I would say that's most dependent on base binder more than aging condition or loading rate or anything. But in terms of formation of cavities, yeah, because the stress strain curve changes a lot. So we do see that. And we've actually seen some binders that the stress strain curve, it's like gets to peak and it's basically like a flat line from peak down. Like it's almost zero post-peak deformation. So we do see a lot of strange things, and a lot of it is adhesion issues in those aged binders.
So did you see much more cavities forming? Like more
In aged binder?
frequently? Yeah.
No, I would say no.
Like the same number?
Yeah, the cavity, like I said, the cavity size and shape and number of cavities all probably depend most on the base binder, choice of base binder, rather than any kind of aging, loading rate, or temperature. A PAV of a specific binder looks more like the RTFO of that binder than the PAV of another binder. So.
One question. For the nanomaterial study, what was prohibiting the dispersion? Because you said for all different testing scenarios, they all clumped.
Yeah, I think it's something inherent in the nanomaterials themselves that just dispersing them in any kind of fluid is just really difficult. Usually people like to use some kind of carrier to do that dispersion, water or flux. But if you use any kind of flux, like we tried this like aromatic flux, it affects the binder properties because you're adding something like viscous fluid to the binder. Water, the idea is that it'll evaporate, but even water we couldn't have work well as a carrier. So I think it's inherent in the nanomaterials and they need some aid usually to disperse, but in my opinion, I haven't seen any papers where they found a good one yet for asphalt. So, yeah.
On
Yes,
this,
another-
on this nanomaterials paper, did you guys use titanium dioxide?
We didn't try titanium dioxide. We tried what we call, they were all oxides. It's the other way. They were all oxides. It was there was aluminum oxide, trying to think, silica oxide, yeah. So and those we called nano silica, nano alumina, nano clay. I don't even know what went into that one. That was a really weird one. And then this nano glass is a proprietary thing developed at UT Brownsville, and they just sent us that material and we're like, try it out. It ended up being actually the best one, like plus 20% elastic recovery. So from a performance perspective, it ended up being the best one.
Would you think titanium dioxide would still follow the same?
I think dispersion would still be a trick. I think you need to add, like I said, you need something else to disperse it. It might show a better performance just because like it's maybe a higher quality material to begin with. So you might see a little bit of a better performance boost, but I don't think you'd really see that. Like with nanomaterials, you're looking for 100% improvement. You're looking for 200%. And I don't think you'd start seeing that unless you had some carrier that's helping it to disperse. So. Yeah, Isaac.
Change the topic.
Sure.
You talked about healing,
Yeah.
which is a very big topic now. So how did you consider the healing whenever you were testing? Like what was the rest period that you did? What was the loading? How did you determine the maximum loading? Did you include also the effect of temperature on healing?
Yeah.
How were these?
So actually, this was very informal. We didn't publish anything on healing yet because we haven't done any formal like experimental matrix on this. Basically, what we consider for healing is just we pushed it until cavitation, and then we just rested it back at the original position, and we just kept watching with the microscope over a rest period. and we would see that damage would generally, you would see those cavities just shrink in size. But then when we had those cracks back here, those cracks just didn't go away. I mean, that was 3 days with 0 applied load, like just returning it to the original position, and we still didn't see those cracks go away.
You mean the fatigue cracks?
Yes, the fatigue crack. This is just this this cracks formed here after 3 days. It's the same cracks. It's the same specimen.
But when you're loading it to the peak and then you're unloading it, you reach the plasticity. I mean, you're unloading, you'll see the plastic damage that happened.
Yeah.
So why are you expecting healing at whenever it reaches the plasticity?
Actually, there were a couple of studies that showed that this. It depends if. So we're talking about plastic and nonlinear is kind of two different things, and it's very hard in asphalt to tell when you reach plasticity and when you reach nonlinear. What is the difference between those? At least we had a hard time characterizing what's the difference between plastic deformation and nonlinear. Damage is easier because you see it physically. But actually what we found, I mean, you can heal damage in asphalt binder, right? I mean, with heat or with those kind of things, you can heal damage, it will flow. In this case, we didn't apply any heat, but we did see those cavities start to change. But it's true, we didn't, like I said, that's why we didn't publish the work, because we didn't do a heavy experimental matrix where we actually looked, like, what does that healing look like from a stress strain perspective too. So we didn't measure the modulus again, for example. Like, I guess you assume, like, if you do some fatigue experiments, if you push it over the peak, then you start to see some decrease in modulus. Then if you're truly healing, you should regain that modulus. So it's not necessarily even healing because we didn't check what's the modulus before and after the test. So that's why I say that part's a little bit fuzzy, and that's why we didn't publish that part yet. But it's just we wanted to get the observable phenomenon, then we can go back and characterize it. That's something we'll be looking at a lot more.
About the FEM, the initial part of the presentation, you said you went and looked at the stresses in the binder, right?
The stress in the binder phase, yeah.
So, and you had the strains in the mixture too?
So we applied a strain to the mixture, like as a bulk strain, right? So when we ended up, we had a little cube of mixture, like that's what we reconstructed from the CT scans. Then we applied like some strain to the sides of the mixture, basically.
So, Cassie Castorena from North Carolina, I think.
Yeah, North Carolina State, yeah.
She's proposing a ratio of strain in the mix and strain in the binder of 80.
Yeah.
What do you think about that?
Yeah, this, actually I saw this, like, she's not the first, her advisor, he put a paper a long time ago on this topic. I think this is a little bit tricky of a thing to, it's a little bit of a issue of how you phrase it. I think it can be up to 80, but the reason they say up to 80 is because, like, they took a couple of different scales and they applied like a macro stress and then measured like the worst case scenario from all scales. So for example, they took like at the pavement scale, okay, maybe in asphalt you can have a worse stress 5 times as much in the, in the certain part of the mix as you do on the bulk from the tire. Then in the mixture phase, you could have a stress, what's 80 divided by 5? 16. So then you could have, thank you, you could have 16 stress in the binder versus the 16 times stress in the binder versus the mixture. So then they're saying, okay, if you compound those two, you get 5 times 16, you get 80 times worse stress in the binder than overall in the pavement structure. Does that make sense?
Yeah, it makes sense. But I was thinking if you had some link between that and your,
yeah,
you saw the same thing, you saw more, you saw less.
Yeah. Well, actually, it's in my thesis, which is not yet available online. Because we're publishing that, and we'll have it in the AM3P proceedings also. I think we saw, again, if you assume that worst case, then we saw more because we went down to mortar scale, FAM scale. Mm-hmm. So actually we saw more overall stress in the binder. But that's again assuming a worst case. So you're assuming the highest possible stress from the pavement structure, highest possible from the mixture, highest possible in the binder based on that. So since we did 3 scales, I think we saw a little bit more. But again, that's making a lot of assumptions to get you there. Do you see what I mean?
Yeah.
Yeah. So I think that's it's fuzzy to say that actually will be observed, but it's true that no matter what, for sure you're going to have much higher local stresses than bulk stresses. And it's going to be magnitudes higher. There's no question about that. Okay. Anything else? I guess it's 1:30.
All right. So
Thank
let's
you so much.
Okay.
Thank you so much for the
Awesome.
engagement the whole time. It's very difficult to do that.